Am I audible? Uh, we'll start in 2 3 minutes. Let's wait for 2 3 minutes, then we'll start. Okay, so let's begin. So, hello everyone, my name is Raja Mukherjee, and I'll be taking this like tutorial for NPTEL course on reinforcement learning. So, like every week, I will be doing a small recap of this week's course, which was covered, and also we will be solving some basic problems related to it. This session is being recorded, so you can later view it on YouTube. Mm, Thank you for joining. So, let's start. So, for week 11, no, we are almost at the end of our like course. So this week was a little bit short compared to other weeks' curriculum, but this one was quite interesting. So last week we came to this uh, paradigm of problems called hierarchical reinforcement learning. Right. We came across two of the solutions. One was options, another was ham. Right. We also came across the concept of SMDP, that is semi Markov decision problem. Right. So what we saw in a semi Markov decision problem, we are associated with another parameter tau, that is the number of time spent before after an action is taken and before the next next state takes another action. So it is based on the time frame up to which an action is being executed, right? We came across a special operator tau. Other thing that we came across was, yeah, types of reinforcement learning problem. So hierarchical reinforcement learning. So one was your hierarchical, another was what, your recursive, another one was your flat, right? So in hierarchical, what we discussed that, yeah, sorry, modular. Okay, just hierarchical, modular, and flat. So in hierarchical, we saw that uh, we have to pass through a certain hierarchy given to go into the to solve this hierarchical reinforcement learning. There is a precedent that this task has to be solved before solving that task, right? So there was a clear precedent set. In modular approach, that is not the case. Each task is solved independently and then it is merged for the complete task. And in the flat, it is how it is that the whole problem is solved on the given context only. There is no sub problems and all, right? So these are the three special mentions that were done last week. So let's now come to what was the purpose of this week. So this week we came across uh, a new domain of reinforcement learning, that is MaxQ. That is MaxQ. MaxQ value function decomposition. Okay, so this is quite uh, close to how your options we discussed. So what were the things that were there in options? In options we had an I, a mu, and a beta, right? So I was a set of states, mu was a policy, sub policy, and your beta was terminating condition, that a certain set of states can be terminating states or not, and it was given by some functions. So it is not that a state can be a part of I, or a state cannot be can be a terminating condition. So there was some predicate like 10% or 20% of the time. If the function is satisfied, then it is a terminating condition will be executed or not. So why what uh, so what how does that help us? That helped us in a sense that you are able to create a specific boundaries between all the sub options and all, between one options and all, into which the problem was divided. You can form a specific boundary partition, right? So that's how your options was defined. Similarly, for MaxQ value function decomposition, we are dividing the entire task into some subtasks, right? So let's dive into it. So what you have here is code MDP M, and you are dividing it into certain sub tasks, M0, M1, M2, m3 dot 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 m, let's say it is mn. So in subtasks, you are dividing a module into m subtasks. Fine. Now these m subtasks, each subtasks these subtasks form a hierarchy of tasks. So it forms a hierarchy of a task. Okay. So let me explain you what do I mean by a hierarchy. So let's look at the example that was specifically given in that paper, Dietrich. It something goes like this. So you have a you have a grid world and you have the taxi problem. So these are the places from where you can where a customer can pick up a taxi passenger. And there are certain directions. There is a grid. So how a grid look like, that's type of grid is there. So the task of the taxi, let's say this is the taxi. The task of the taxi task is to ferry the passenger from one location to another, right? And also passenger can be picked up only at locations R, G, P and Y, right? That was the basic task in that problem, that you have a taxi and your task is to ferry the taxi from one location to another, and it is a grid world. Like other grids, there are also some obstruction and all. Also the catch was that you can pick up the passenger only from one of the R, G, B and Y locations, not any other locations. Those are the particular locations you can pick up. Right. Now our the actual paper of Dietrich was prepared to solve this task using a this max q function function variable decomposition method. So it prepared this problem in a hierarchical task. So let us represent this in a hierarchical task. So let's say this is the first. So we'll try to draw a tree structure, tree kind of structure. So this will be the entry point, that will be root. So here will be the entry point. Now there are two tasks it can do. Either it can get a passenger or it can put a passenger. Right. These are two tasks it has. Now, what should be the now what will be the subtask of this get and put? What will the subtask of this get and put? So the subtask will be pick up or navigate right. So what is a pickup and navigate? So pickup is, suppose your car is currently here, so it has to pick up a passenger from B. So what it needs to do, it first needs to navigate through a location to this place, and then it has to pick up. So that's how we are breaking the two tasks. No, let me define one of it first, then I will come to drop. Okay, so one of its task is pick up, right? So for picking up, what it needs to do, it needs to first navigate to the location where the passenger is, and then pick him up, right? So that is that is one portion of the task, right? And when it needs to drop a passenger, what it will do? So again, it will first navigate to the location. Suppose our passenger wants to go, it's currently at B, and it wants to go to some place at G. So first, what will it do? Y. Suppose, so first, what it will do? So first, it will navigate to that location, and then he will drop him off. Right. So then he will drop him off. So that will be the other graph. Right. So this is the subtasks now, right? Pick up and navigate, or navigate and then drop. Right. So these are the tasks the taxi driver has to do. Now navigate can be of four types, right? It could be north, east, west, south. Right, these are the four kinds of navigation the taxi can do, right? So any other task remaining, or I have covered all of them? So navigate will also come with some parameter like where to go and where to go, and that's all, like what distance to travel and all. So it will come up with some parameters, right? Let's let it be t some parameter, different kinds of parameter. It could be one parameter, it could be a list of parameters. Now the question arises, suppose you have an MDP. What does the MDP consist of? What does the MDP consist of? MDP consists of a state, action and reward, right? It consists of a state, action and reward, right? Yeah. So in this graph below, how will you how will you relate? How will you relate? So this is an MDP, right? This was one whole problem. We had converted into some hierarchical tree structure. So how will you relate this with an MDP with this graph structure? How will you relate with it? and state, get, put, and nothing else. Yeah. Uh, yeah. So let me help you. Okay. So I will use a different color. Okay. So a max queue consists of three things. One is your state. Number two, subtasks. Number three, reward. Okay. So now let me define each of them. So let's come first to this portion, subtask. Let's come to subtask first. A substack task can one be a composite action. Okay, let me just not use such a bigger term. Can be either a subtask itself, or it can be a primitive action. So I will now reorganize this whole graph to give you a difference, what is a subtask and what is a primitive action. Okay, so I will little bit remove some things from here. So here it is, pickup. Pickup is a primitive action, a terminating action. Okay. It is a primitive action. North, like go north, let's say, is a primitive action. South, another primitive action. east and west other primitive actions, and similarly drop is another primitive action. So primitive actions are the one which will you physically do. Okay. Now, what is a subtask? You see, this is a subtask. Get a passenger, put a passenger, or navigate. These are three called subtasks. So these are subtask, and this is primitive action. And one important thing you need to remember is primitive action is a special case of subtask. Okay, so primitive action is a special case of subtask. Also, from now, you can understand that leaf nodes are basically your primitive action, and other nodes are basically your subtask, right? This could be a great observation, right? Like your leaf nodes, that is pick up, this north, south, east, west, drop. These are your leaf nodes, right? Doesn't have any child children, so these are all your primitive actions, and your subtasks are basically get, put, and navigate, right? So this part is clear how we are converting MDP to this. So another thing, let's complete this part also. So what is substate? So each max queue, so each subtask or so let me just delete this and write something like this. Each subtask, let's call it mi. So this is your task m. It is divided into m0, m1 dot dot dot, mi dot dot dot, mn. So each mi consists of number one, state, si. Si is basically a subset of all the states S. Si is basically a subset of all the states S. Number two is your subtasks, also known as child subtasks. Child subtask and primitive action. And number three, your reward. Right. So these are the three things which you have. Now again, let's come back to this one. Let's concentrate on this one. So What are its what are its subtasks? What are its subtasks? So what are its subtasks? So it has a subtask called navigate, right? It has a subtask called navigate. It has a subtask called navigate, and it has a primitive action called pickup. Right? It's very simple to notice that it has a subtask called navigate and another primitive action called pickup, which are both are its child. And going from what do we mean by reward? So going from this to this, like any your any MDP problem or your any uh, or your any machine learning any reinforcement learning problem from one state to another, whenever you do a jump you get a reward for it, right? So that's what it is. Another thing is this substacks mi, these subtasks mi is called is not called is SMDP. So this also consists of some terminating states. Notice, like, unlike options, there are unlike options here we have actual terminating states with probability 0 or 1, right? So here we have, unlike options, where there was a terminating condition, that if that condition is matched, then only that state is considered as a terminating state. Here it is not. Here we have specific terminating states. Okay, so in order to solve the MBT this max q problem, so this one is called, this root node is M0, the first machine, right? So first M0 happens, then either you do a get or a put call, and then you do the rest. If it is a put, then first you navigate and then drop off. So you know tree traversal, right? So this traversal is kind of like a tree. So suppose if you follow this path, it will first go here, then it will come back here, then if it has to do some other task, you will go there, and then, so it is basically a tree traversal. So if you remember tree traversal, it continues to do a tree traversal. So tree traversals are used kind of like child, then like left right child, or those kind of things, left center child and all. So here also, if it once goes through the goes to the terminating not the primitive action, once it selects a primitive action, then it's come back to the to the subtask before it, to check if any other action it needs to take, and so on. So there is a feedback. That's why there is a difficult part. It traverses just like a tree traversal. So any doubt regarding this? Okay, so let's go. So next what we will do is, so I guess by now the algorithm should be a little bit clear to you. So if I begin at m0 and then execute m1, m2, m3, then again we will come back to m2 to check. Let's say m3 is a primitive action. So we'll come back to check that at m2 that if there are other actions, other subtasks to be done or not, or other actions to be taken or not. If it is once that is completed, we'll come back here and last come back here. So we start at m0 and we aimed at also m0. Correct. Now so for this MTP, so what do we learn here? We learn an hierarchical policy pi is equals to pi 0, pi 1, pi 2, pi n. So we learn a hierarchical policy pi 0, pi that is basically divided into semi policies. So it corresponds to the hierarchy you have m0, m1, m2, m3 dot dot dot. So what will this one give me? So let me define a term. Okay, first let me define a term v pi I of s. So what does this mean? V pi I of s. So so it means so s is some let's say state, s some state belonging to s belongs to capital S. V pi I of s what it is expected to return at state S after executing subtask I. correct? This is what it means. So this term, so remember this definition, this is the definition. So v pi I of s suggests that expected return, so v is your value function, that is your expected return. So v pi I of s suggests that you are at currently state s. So previously what you had, you know this value, this value, right, v of s, that is expected return at state s. What we have here is that another, that you are at a subtask, you are inside a subtask. So what we are saying is v pi I of s basically refers to return at state s after executing your task I, when you are executing task I. Okay, so let's dive into it again. When executing task I, what can task, let's say, mi have? So think about it. What can mi have? Mi have either a child subtask or a primitive action. So mi can have either a child subtask or a primitive action. Right? These are the two things it can have. Also remember what we have here. So this mi consists of subtasks, right? So also remember this is an SMDP. So these all subtasks are SMDP, since all of them have a terminating condition. So given it is an SMDP, what we also have? We have all the distribution properties, right? You also know this task. We also have this distribution probability with us. Right. So our goal is to find this, what it will be. So you have previously. So shall I give you the previous value function? Then it will be easier to understand you, right? So what was the previous value function we have? V pi is equals to, what was the previous value function we had? V pi is equals to pi of a right. This is what you previously had. Right. This is your value function which you had for MDP. So now V pi I comma s. So also this means that we are applying. So also this means that we are applying policy pi over I. over state I, right? Now, one thing you will tell me that weren't we applying policy pi I? Weren't we applying policy pi I on state I, right? This could be a question for you, that we are applying pi I to state I. So, why are you not including uh, pi I directly? That instead of writing pi, why are you not writing pi I? The simple reason is that the hierarchical policy actually is divided into certain small policies that you have uh, that 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 you have it depends on how you have divided your uh, tasks, right? So it depends on it. So our task is now to find VIS. So when you are obviously VMI will either have a child subtask or a primitive action. Let's the child let it be MA. So let's the subtask we are MI executes, like, so after MI, let's say we have MA, right? So we will try to execute MA, right? So what will you have? So obviously, so we are making a jump from I to A. So we should get some reward, right? Previously, we have seen that when you are moving from one state to another, similarly, we are moving from one task to another. So we should get some reward for it, right? So what is the reward we should get? So what? So my question is, what should be the reward we are getting out of S, comma A? So what should be the reward you are getting? So suppose you are at state S and you are getting an action A, like, yeah, that is you are moving to state A, right? So what is the reward you should expected reward you should get? What should be the reward you get? Also remember, when you are moving from MI to MA, so this is a terminating condition, right? So at a terminating condition, what reward you get? So previously you have explored Monte Carlo and all. So suppose A, B, C, D, dot dot dot, A, G, and let's say T. T is the terminal condition. So when you get T, you get a reward for it, right? You get the immediate reward back from it, right? So in a similar way here, RSA is basically equal to V pi A given S. That is, what does that mean? That given S, whatever value function you generate after executing action subtask K, after executing subtask K, whatever value you are generating, that is your reward for selecting action A for emit. from mi selecting subtask A. Here remember these A are not action, these are subtask. And it could be primitive action. Right. So get this thing cleared, like what I have said here. If it is not clear, just tell me, I will again explain. Yes, yes, you tell. You can ask also if you have to want to save time. So primitive action and subtask, the rewards are same. Exactly not. So primitive action, you will get a different set of reward, right? So if you are executing a primitive action, so this v pi a of s, what it will be? Technically it is yes, but the immediate reward will be different. So what it is here? Here it is an expectation. So here this value is an expected reward, right? Right. That will always be different. So you are asking me that will the rewards be same? So are primitive action and subtask same? Primitive action is a special case of subtasks. Is a special case of subtasks. Your subtasks may consist of even more tasks. So basically, what happens here? If you come back to here, suppose first you get to get, right? So either it could be a pickup or it can be a navigate based on what action you have been given. So if it is a get, it does this primitive action and it gets a direct reward. But if it is not a pickup, what it do? It goes to navigate and this goes to one of these direction, north and south, right? So once it gets north, it gets a reward. It comes back here. So that's how it is accumulated, and then again it comes back to here, and then that's how it is accumulated. So this is what you have done previously, the accumulation of rewards. The concept is exactly same. Right. And that's exactly what we are doing here. So now let's come back to this. So our goal is to find v pi I of s. That is, what is the value function at state s for subtask I, for subtask I. What is the value function? So from at so let me remove this. So this, if you remember, so you have an immediate, so I just written it just to remember you what we do here. So we will take the immediate reward for action A, and then we calculate the reward for all the subsequent value functions, right? So that's for showing that reason I wrote it. Let me remove it. We will write v pi I of s as, so currently we are mi, and then next subtask is, let's say, ma or some subtask. So it depends on basically policy pi, right? So we will write it as r of s comma pi I, that is policy I. What should we select? So the policy could be that select this first and then this, or select this first and then this. So that upon how policy depends, we will not think about it now. Plus it will be summation st comma tau p pi I s dash comma tau given s comma a, no sorry, given s comma pi I sorry, I made a mistake here. Pi I s, that is the policy I am taking for state s. Pi I s v pi I comma s is equals to v pi r bar s comma pi I s plus s dash comma tau v pi I s bar comma tau slash s comma pi I of s gamma tau v pi I comma s bar. Right. So let me just explain it one by one. So currently at state I, so we will apply this policy pi. So we know as m consists of m0, m1, m2, mi, mn, and similarly pi consists of pi 0, pi 1, pi 2, pi I, pi n, right? So currently I am at subtask I, that is policy pi I, we have to select. So we select policy pi I, and also at code MDP step is. So based on it, what we will do, we will select the next state what it will be, next subtask what it will be based on this policy I. Okay, so that's the reward you get. So this will actually be v pi pi I s comma s, right? This is what it will be, plus your transition distribution, and v pi of I and next state. What will be the next state? Right? That is A star. A star is the next state. So just like normal transitions, this function exists. Right? So any doubt regarding this equation, you can ask. Next, I will go to the Q update function, QRL function. Okay, so let's go to the Q function update. So the Q function is given by this Q of pi I comma s comma a. So what is s? So we are making a transition from mi to ma. So that is the reason we are writing s. Right? Previously we don't know what is the transition. It depends on the policy pi 1. Right? So here we know it. So it is not going to be an issue. So it will be v pi a of s plus, this part is crucial, s dash tau p of pi I s dash tau s comma a gamma tau q pi I of s dash pi of s dash. So this function, so this function is quite understandable, and it's frankly comes directly from the previous function which we discussed. So here, since it is a value function, what we have considered it for all the policy pi, that's what we have done here. But here we have a definite policy, so we know we are calculating it for certain subtask A. So that's why we have written it like this. So now this part has a special significance. The significance of this part is known as expected return for completing mi after ma terminates, which is known as which is called c pi I comma s comma a, right? So this whole part, what it says that first we are going to mi to ma, right? So when suppose it makes some weird transitions back, right? So it does all the computations after ma. So let's say it goes to mx or something, and then it ultimately comes back to ma, and then it returns to mi. Now mi also have some states after it, right? Some maybe some other steps like mj, mk, something that occurs after it. You needs to complete it, right? After ma. So that part, what is the expected reward for completing that after ma terminates, is what this guy gives. This function, this parameter gives c pi I of sa. That is basically this. So to reframe it again, let me come back to the example. Okay. So currently you are in at gate. Okay. Gate has two parts. So the policy first says, let's say the policy currently says that first go to navigate. Navigate completes east, west, north, south, whatever location, and then you come back, then you do pick up, right? So in that case, what will happen? In that case, this relevance starts. So you are in gate A. So let's say in our case, this is mi. You complete so, and this is ma. So let's say this is ma, this is mi. So you complete all of this, but you also see you have another thing left after completing ma, another child left. So let's say this is mp. So you will first complete ma, and then do mp, and then your task is completed. So that is the return. So what is the return from this? That we are what is we are computing here. So any doubt regarding this? So technically q pi I s a is given as v pi a comma s plus c pi I comma s comma a. Okay, so this is your ultimate function. So any doubt regarding so far you can ask. Yeah, you can speak also. No issue.
Yes, sir. This so similarly we are because since it is like looking like a decision tree kind of structure. So
Yeah.
this
No. So decision tree is one way path, not a return path, right? Do you return in a decision tree?
okay, okay. So this formula, the q of I equal to v of I plus c of I, will also applicable to when you are at the root node. Like right
Yeah,
now we are
I will come back to it. I will come back to it. So
okay.
so so
Right,
so
right now we are at the leaf, and then we are
so right now you consider that you are currently in some place here. You are currently some place here. So what you
correct,
will,
correct,
so you will do to navigate. So this is, let's say, ma.
correct.
So this also has its child. It does all sorts of fancy stuff here based on the policy pi. Then it has to come back to it, and based on the policy it has to execute this, right? So this part, this part basically tells us about what is the expected return after MA is completed.
Okay, and then this will keep on adding until we get to the root.
Yeah.
Right?
Yeah,
Accumulated. This
yeah,
value is
yeah,
accumulated. B5 and C5 is accumulated.
yeah.
So
So let me rephrase it. So this is for a certain action, right? So this is for a certain action. So so here CPI will be something like this. So this is your MI. So this is your MI. Yeah, yeah, nothing fancy. Yes, that's what I said. Yeah. Okay. So after finishing this up, it will go to the other parts of here. So we will come back to root now. So this is understood, right? You have understood this, right? Yeah, fine. Okay. So always remember. So we discussed, right, that uh, we discussed it here, right? So you have M0, M1, M2, M3, and various one. So always remember, your task starts at M0 and ends also at M0. This part is clear. So you hierarchically you go down, 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 right? And you start to catch up the results back, right? Try to get the result back from the leaf node, and ultimately you accumulate the result again at the root node, and that's how you get the total value, right? So if you are at M0, suppose you have given a task that, so let's say the task is that you first go to R, pick up a passenger, then go to G to drop the passenger, then from G pick up another passenger and go to B. So let's say that is one of your policy. Then what you will do? You will come first here, then put, then get, then navigate, then pick up, then again come back to root, then again you will do the put, drop and all. So it goes on as on a basis of traversal of the graph. Like, so at the end of the day, your task ends at M0. Whatever your whatever policy you have specified, whatever policy you have done, so it ultimately ends back at your root, whatever trajectory you have started and all. It ultimately ends at root node M0. So if you have to calculate the value function, total value function, how will you do it? Right? We will use this simple formula. Okay. So let me write it down. So it will be V pi. You are currently solving M0 and you are currently at state S. This is value function for all state S, right? So don't worry, it can be tabular or not, it is not an issue. V pi an s plus c pi a n minus 1 is s of s a of n plus dot plus s pi a1 is a2 plus c pi 0 is a1, where v pi an s is equals to pi of s bar p s bar s comma an r s bar s comma n. So let's explain it. Let's have an understanding of this. So basically, so you are starting at some route one here, and you make some navigation to some part of the country here and all in this tree structure. So this part is when we have hit a primitive action. We are assuming, let's say we have a trajectory like a1, a2, a3 dot dot dot. An is the last one and an is a primitive action. Hit a primitive action. Right. So we add the value of the primitive action to it, and then we try to round it up, right? We try to come back one after the another, one after the other. We just uh, accumulate uh, back, and that is what this gives. This is one step back, then there will be two step back, and then it is one step ahead. Just one step ahead, we are doing it. Okay. So this is quite simple to understand, that once you hit a primitive action, you can try to compute backwards, and there this part comes, this C and all. So any doubt regarding this, you can ask. This part is similar to how previously you have seen the reward structure and all. There is nothing difference here. How you are calculating the rewards and all those things. Okay. Now, what next? So how will you set up the algorithm? Algorithm is pretty simple, right? So you have your policy evaluation and policy interval. So you do this kind of whenever value function comes, there is only one algorithm. Uh, the only difference is how you are computing the value functions, right? Like TD0, there is one type of computing the value functions. At Monte Carlo, you have another form of computing the value functions and all. But other than that, the algorithm is quite simple. You first evaluate, and then you improve it, right? So similar structure you will follow here also. I mean, every algorithm is same. Like first evaluate and then improve. Okay. And there is this pseudo reward concept, that is basically your part where inside inside the like, that's how a system designer works, like for specifying your subtask, how you are specifying the subtask, like how you are moving from one task to another, some extra part, but it is not much important. Like what we discussed here, we assume that pseudo reward is 0, that is called max q 0, and there are some other functions there which describes it, but it is not much important needed now. Okay. So let's now come to this week's MCQ problems that we will solve. So using max Q approach leads to solution which are hierarchically optimal, recursively optimal, flat optimal. So what will be the answer? Hierarchically optimal, recursively optimal, flat optimal. Why hierarchically optimal? Are you sure it is hierarchical optimal? It may seem to you that we are doing hierarchically. Are we doing hierarchically? I will ask you to look in this diagram and look at this part specifically. So so there is no, if you look at the navigate part, you can what you can do is you can just find a local minima for it and then use it, right? You don't have to think about it, like who is calling it, like either put will be the next one or not, right? So that's not something you care about. You care about finding an optimal navigation system from one portion of the grid wall to another portion of the grid wall. That is the goal of the navigation system, to find out. You takes a parameter and all. So it is a individual system and which doesn't depend on get or put. So yeah, so this one is recursive. So you also see the so I gave you an example last week. What about hierarchical? What was that? That suppose you have a room, from you're going from room 1 to 2, and there is a small the question given is that you have to go through, say, like there are two doors, door 1 and door 2, and it is told that you have to go through door 2 to room 2, right? So okay. It's better that I draw and explain it. So what was the previous week's question? So suppose you have this structure, so this is R1 and R2. So this is the final goal destination you want to get, and this is the start destination you want to get. So suppose you have been given this condition that, so this is D1 and D2, go to R2 through D2. So then there you have a hierarchical situation that you have to go through R2 there through D2, that you have to go through D2. So you have to go through this one. So what you will find is, even if your start is here or here or here, so you will always have to go to D2 and then you go to D1. So the objective of task 1 is that find an optimal route to D2, not an optimal route to DR2, and then, right? So that there a hierarchical setting is comes up, but here you don't have that. Here you have a recursive one, and just like a recursive call, so when you do a function call, what happens? After you call the function, you get something back, and then you do it again, right? So here also you are doing it same, right? So here, let's say navigate is a function call. You call it, you do some task, and you come back to the get function, and then get again do it. So it is a recursive. So it is a recursive optimal. Clear it is now. Okay, so let's go to the next one. So we saw that each subtask has an associated pseudo reward function. Are the rewards of the core MDP available to the agent when it is learning policies of individual subtask, or is the agent restricted to the corresponding subtask pseudo reward? We haven't discussed this much, but let's do it. So when we are discussing the taxi problem, when we are discussing the reward, which reward we are considering? Only the core MDP reward, or yeah? So whatever we have discussed so far, we are only considering the core MDP rewards. So in this case, we were getting a reward when we were hitting a primitive action, right? We are getting a reward when we are getting a primitive action. But what will happen in pseudo reward, that extra term will be added for each subtask has an will have a pseudo reward function. So in that case, we will consider both this r plus r bar to it. So the correct answer is both pseudo reward and core MDP rewards are available. Okay, so let's go to the next one. So in a max Q formula, is termination in the subtask deterministic or stochastic enough option as in the option framework? This should be easy. Why it should be deterministic?
So because like this, the leaf nodes are almost like it cannot be a stochastic because you already know that the sequence.
Yeah.
So
So the correct answer is it is deterministic. But why it is deterministic? Because in options, what we had, options we had a beta function. So we used to test with the set of states in I, right? I had some states like I, mu and beta. So with the states in I, we used to check that whether a certain state S satisfies the termination condition or not, and then only we are trying to figure out whether it is a terminating terminating condition or a terminating state or a non-terminating state. Similarly, similarly, here what we have, here we have in M, in my what we have. we have a set of subtasks, right? And you have a set of sub states SI union TI, and also what you have is a terminating state. So this TI, and then you have viewered, so that's one. So this TI are the list of terminating states. So here you don't have any something like beta. So either here whatever states you have, you are either 0 or 1. So if it is 0, that means it is not a non-terminating state. If it is 1, it is a terminating state. There is nothing, it is all black and white. There is nothing in between. Okay. So let's go to the next one. So each subtask I is an SMDP because the state space of the subtask is a subset of the state space of the core MDP. Each subtask has its own policy. The rewards received in subtasks depend not only action in the subtask can be temporarily extended. The rewards in subtasks uh, depended not only on the state but also on the subtask in which the action was executed. So why we this MI is SMDP? So what does SMDP have? Oh, sorry. Sorry. Yeah. So what does SMDP have? So SMDP has also already. So what do you consider in an SMDP? SMDP basically has a component tau, that is a random number indicating the length of the action, right? So what does a subtask is? What is a subtask in an SMDP? So subtask as the name says, it is a subset of the task. It can be a subtask or a primitive action. So what is the primitive action? Is actually the action, right? So you see, when you are initiating an action, when you are in this case, what happens? When you try to initiate actions, it passes through various subtasks and then it reaches the primitive action. So this diagram is the best diagram to explain. So suppose you are starting something here. What color should I use? So suppose you are starting something here. You are trying to extend some action here, right? Let's say go to south, right? Go south, right? So what happens in this case? You first go to this subtask navigate and then you go to south, right? So your action was go to south, but it now is divided into a much larger form of action. Whereas you first do a subtask, that is navigate, and then you take the action, right? So here comes the tau. So how long your subtask is required, so how much time your execution of the subtask is required, that is your tau. So that is the variable that you are adding, that portion you don't know. So tau in subtask is basically time taken to execute a task, right? Execute a subtask, sorry, execute a subtask. Right, so the correct answer will be this action in a subtask can be temporarily extended. So your action is basically getting rolled out into many subtasks and finally reaches the primitive action. So that's why it is an SMTP problem. Clear this part? Okay, so let's go to the next one. So suppose, so the expected reward function uh, r bar s of a correspond to the subtract is equivalent to VISI. So what it is saying is r bar s comma a is equals to v pi on pi a comma s. Is this correct or not? Is this true or false? Why it is true? Why it is true? Yeah, so my question is like, how can you determine that which state? How can you determine? How could you confirm we
So
reached?
they have given some certain states. I think I didn't. Okay, eight is the eight is
No, no, not eight. This is
yeah,
S.
eight, right? Eight, no? Yeah,
Yes, 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 yes. So how can you confirm that we reached MA from MI by looking into this part? By looking into this part, how can you confirm that we reached MA from MI? There is no guarantee that it comes from MA to, so that we are currently in state MI and went to uh, MA. So that's why we use the term pi. because it is the hierarchical policy, and we know that that is the policy we are following. So that's why we use pi in that case. Pi is basically your divided of uh, pi 0, pi 1, pi 2, dot dot dot, and pi n. So that's why we use pi. Okay, so let's go to the next one. So in max q approach to solving a problem, suppose subtracts mi invokes subtracts mj. Do the pseudo reward of mj have any effect of on subtask mi? So we are saying that mi is invoking mj. So we come from mi we go to mj. So we are saying that pseudo rewards of mj have any effect of mi. Yeah, you are correct. Correct. You're correct. So uh, so pseudo rewards are independent of each other, right? Pseudo rewards are independent of subtask, right? But what happens in this case is you compute the value function of mj. So you will include the pseudo reward here, right? And when you are trying the policy of mi, what you will do in that case, you will just add it up. You have to add it up this policy which you have got from here, and that's why mi depends on the pseudo function of pseudo reward of mj. But not the opposite is not true, because mj doesn't have any, mj doesn't invoke mi, but mi invokes mj, so that's why it will have an effect. So correct answer is yes. Okay, so any doubt regarding this you can ask. So this was the last slide for today. Okay, so thank you for joining. We will again meet next week, the last class.
Thank you, sir. Thank you so much for your time. Yeah, I
Yeah,
really appreciate it. Yeah,
yeah.
thanks.
Thank
Thank you.